Okay, get this. What if I told you that the simplest shapes you can imagine, a cube, a pyramid, even a soccer ball, are all hiding a secret, a single mysterious number that basically defines who they are? It's this incredible link that connects something as simple as counting corners to the very fabric of space itself. So take a look here. We've got a simple cube, a classic pyramid, and then this way more complicated thing, a dodecahedron. On the surface, I mean, they couldn't be more different, right? But believe it or not, they all share this one secret property, a single hidden number. So what on earth could it be? All right, let's start with a classic, a cube. It's got 6 faces, 12 edges, and 8 corners. Pretty straightforward stuff, right? Just keep those numbers in your head for a second. Okay, next up, a pyramid. This one's a tetrahedron, to be specific. It has 4 faces, 6 edges, and 4 corners. Now hold on. Those numbers are totally different from the cube. The plot, as they say, thickens. And just to show you this isn't about simple shapes, here's a dodecahedron. This thing is a beast. 12 faces, 30 edges, and 20 corners. The numbers are just all over the place. So what is it? What could possibly connect these 3 wildly different objects? Well, the person who cracked this code was the brilliant 18th century mathematician Leonhard Euler. He realized the secret wasn't just in the number of faces or the edges or the corners alone. No, he found a relationship between them, a stunningly simple formula that just unlocked the whole thing. And this is it, seriously. It looks almost too simple to be this important, but it is. You just take the number of vertices, the pointy corners, subtract the number of edges, and then add the number of faces. V minus E plus F. So, come on, let's apply this rule to our shapes and see what happens. So let's run the numbers. For our cube, we've got 8 corners minus 12 edges plus 6 faces, and that equals 2. Okay, what about the tetrahedron? 4 minus 6 plus 4. Whoa, it's 2 again. All right, no way. What about that crazy dodecahedron? 20 minus 30 plus 12. You guessed it, it's 2. It's incredible. It doesn't matter how complicated the shape is, the answer is always the same. And there it is. The secret number is 2. For any simple shape, and by that I mean one you can kind of squish into a sphere without ripping it, the number of vertices minus edges plus faces will always be 2. And that whole no holes part, that turns out to be the key. And this isn't just some neat mathematical party trick. This number, it has a name. We call it the Euler characteristic, and it tells us something incredibly deep about the fundamental DNA of a shape. It's topology. But trust me, this is where things get really interesting. So this brings up a pretty obvious question, right? What happens if we break the rule? What if we change the fundamental shape? What if we punch a hole right through it and turn it into something like a donut? Does our magic number 2 still hold up? Not a chance. It changes completely. You see, this number, the Euler characteristic, you'll often see it written with the Greek letter chi, is what's called a topological invariant. That's a fancy way of saying the number is baked into the very essence of the shape. For any sphere-like shape with 0 holes, it's 2. But the second you introduce 1 hole, like in a torus, which is the math name for a donut, the Euler characteristic plummets to 0. The number is literally telling us about the holes. Okay, so we've connected a simple counting formula to a shape's basic structure. That's already pretty cool, but hang on because the rabbit hole goes way deeper. There's an even more mind-blowing connection hiding here, one that links this discrete world of counting corners to the smooth, bendy world of geometry and curvature. And here it is, the big reveal. It's called the Gauss-Bonnet theorem. And honestly, it's one of the most beautiful ideas in all of mathematics. It says that if you add up all the curvature across an entire surface, every single bend, every single curve, the grand total is directly locked to its Euler characteristic. It's telling us that counting and bending are just 2 sides of the same coin. And this is the wildest part. Imagine you have a perfect sphere. Now, imagine you put a big dent in it. The local curvature has changed, right? Some spots are flatter, some are more curved. But this theorem guarantees that as long as you didn't tear a hole in it, the total amount of curvature over the whole surface remains exactly the same. It just redistributed itself. Because its topology, its Euler characteristic, didn't change. And we can even put a number on it. For any sphere-like shape, because its Euler characteristic is 2, the Gauss-Bonnet theorem tells us its total curvature must be a constant value, 4 pi. It doesn't matter if it's a perfect sphere, a lumpy potato, or even, roughly speaking, your head. If it has no holes, the total amount of bend is locked in at 4 pi. Now, remember our donut, the torus? Its Euler characteristic is 0. So what does the theorem predict its total curvature is? You got it, 0. But wait a minute, how can a very obviously curved object have 0 total curvature? That sounds impossible. It's this beautiful, elegant balancing act. The outside of the donut, the part that curves like a ball, has what we call positive curvature. But the inside of the hole, the part that curves like a saddle, has negative curvature. And it just so happens that these two values, the positive and the negative, when you add them up across the entire surface, they perfectly cancel each other out. The result is 0. Now, I know this might all seem beautifully abstract, but this hidden rule has very real and actually very surprising consequences for objects that we see in our everyday world. Let's look at one you've definitely seen before. A traditional soccer ball. It's basically a sphere, which means its Euler characteristic absolutely must be 2. Now, if you try to build a sphere using only hexagons, it won't work. It'll stay flat. To get the shape to curve and close, and to get v minus e plus f to equal 2, the math itself forces a rule on you. You must use exactly 12 pentagons alongside the hexagons. Not 11, not 13. Always 12. This deep, abstract mathematical law literally dictates the design of a soccer ball. And that's really the ultimate takeaway here. Euler's simple little formula isn't just about counting things on a shape. It's a key. It's a secret bridge that connects two totally different mathematical worlds: the discrete world of counting corners and edges, and the continuous, smooth world of geometry. It shows us they were connected all along. So it just leaves you with this final thought. We started by counting corners on a cube, and we ended up with a fundamental law of curvature. It really makes you wonder if a number as simple as 2 can hold such a profound secret about the nature of shape and space. What other elegant hidden rules are just out there, governing our world, waiting to be discovered?